Hi, my name is Hatem Al-Tayef. I'm the principal research scientist working at the Extreme Computing Research Center at KAUST. I'll be talking at the ARM HPC user group held in conjunction with the ISC21 High Performance Computing Conference. I'll be talking about meeting the real-time challenges of ground-based telescopes using low-rank matrix computations. So I'd like to start with some acknowledgement. My colleague from KAUST, some collaborators from institutions in astronomy worldwide, and also vendor partners from ARM and Fujitsu. So at KAUST, we've been supporting several major ground-based telescopes, including those from the European Southern Observatory, the Very Large Telescope, and the European Extremely Large Telescope. We've been also working closely with astronomers from Japan, in particular working with the Subaru telescope located in Hawaii. So those ground-based telescopes basically host instruments, and those instruments basically are in charge of deciphering the light coming from remote stars. With that light, they are able to identify what constitute the atmosphere of those remote galaxies and stars. In this talk, we'll be looking at the MAVIS instrument, and we'll be discussing how we are able to accelerate the real-time process of the simulation in this instrument. The common denominator for all of those instruments and ground-based telescopes is this atmospheric turbulence. All right. So, the picture that you see here is taken with a compact camera, and you can see how the sun is being blurred around its contour, and the atmospheric turbulence basically disturbs the trajectory of light rays and reduces, as you can see, the astronomical images quality. So this is a big challenge for astronomers. And the idea is how to compensate for that atmospheric turbulence so that they can get a clear image out of those telescopes. Adaptive optics approach come to the rescue for those giant telescopes. And the idea is that they have some tiny deformable mirrors deployed on those telescopes that would tilt in a certain way and direction to compensate in real time for those atmospheric turbulence. Those tiny deformable mirrors are being commanded by actuator, and those actuators are being themselves, commanded by a real-time simulation, right? So you want to basically correct in real time or compensate in real time for those atmospheric turbulence. And the next slide here show a 2D view basically of this deformable mirror and the actuator, which correspond to one of the key hardware components of those telescopes. And so those actuators are going to pull and push those tiny mirrors in real time, to compensate for the turbulence, atmospheric turbulence. And so what MAVIS is doing, MAVIS is a third generation instrument for the Very Large Telescope. It's an imager and spectrograph fed by a multi-conjugate adaptive optics. So the idea behind MAVIS is really to scale up the whole adaptive optics concept by having more actuators, providing faster control system and better calibration. So all in all, it's a deeper and sharper than any space-based instrument. So if we look at the matrix of measurement taken or generated for MAVIS after tomography and predictive control, its typical size is 20K by 5K. 20K is the number of measurement coming from the wavefront sensors, and the actuators are 5,000 here in this particular case. And when you look at this matrix here, which is short and wide, you can see that the magnitude of the various elements of that matrix they are very, they vary with a certain range. And some of the range actually lead toward very small elements. And the other aspect is how the structure of this matrix can be exploited. And if you were to zoom in further, one can really identify here a structure that may be actually linked with the system parameter of the instrument. And if you take that matrix, a sample of it, and you basically tile it, you split it into two-dimensional tiles, and you do a singular value decomposition just to identify how much information is important to keep within each of those tiles. You can really realize that we're dealing with a matrix that is data sparse, a matrix that conveys sparsity in the data, contains sparsity in the data. So there are clearly opportunity for low rank approach, and this is something that we want to leverage. And the idea is, once we have identified this data sparsity in this measurement matrix for MAVIS, which actually may also apply beyond that instrument, and other instrument can be also impacted by this current work. We actually can perform a matrix vector multiplication that used to be performed on dense matrices, now can be done in a compressed data storage called TILE-RANK. And the idea behind TILE-RANK is, I have my dense matrix here, which is a 4x6 tiles, and I'm trying to do a matrix vector multiplication. And this is what I have to do in real time, millions of times in the course of the night while doing observation. So what I do is I do a compression on each of those tiles individually. I can use any SVD-like algorithm, for instance. And by doing this compression on each of those tiles, I move from a dense storage to a compressed storage with the U basis and V basis, right? And now I need to do a matrix vector multiplication by leveraging that data structure. So what I do first, I stack the bases. This stage basically take all the bases, stack them together so that we have a better memory access and have a better locality. So once we stack those bases, the U and V bases, I can now perform my matrix vector multiplication. I start with the V bases and I multiply those V bases by my vector X, and I obtain this vector YV, which is a transient vector after doing this first stage. And this is basically done by doing a batch matrix vector multiplication. The fourth stage basically take the YV transient matrix and do some projection into the U basis. And I get this now YU data structure. And with that YU data structure, I can perform my last computational stage here, where I multiply this YU, I multiply the U basis by this YU transient matrix. And I get at the end basically my Y vector. And that operation here showed by those green circle is done again by a batch matrix vector multiplication. So we go from a dense matrix multiplication, dense matrix vector multiplication with a single call to level 2 BLAS to a batch, a series of batch matrix vector multiplication to leverage basically the TILE-RANK data structure. And all this rely on batch matrix vector multiplication calls with variable sizes, because the rank that are captured for each of those tiles may be different, from one tile to another. And now if I apply this technique on the MAVIS instrument using a real data set, I look at the numerical accuracy assessment. This is a heat map showing 3 dimensions, the accuracy threshold versus the tile size. And, the stray ratio gives the color. So the stray ratio, the higher, the better. And what you can see here is that for an accuracy of -4, we are able to get the stray ratio, which is green, which is a good indication that for a tile size of 128, I'm able to get a stray ratio close to what I would get if I won't do any approximation. And on top of that, the number that is being reported here in 3.6 here correspond to the speed up. This is the theoretical speed up by after doing compression. This is the number of operation savings that I'll be able to perform by doing an accuracy of -4 with this tile size of 128 and achieving close to 14% stray ratio. Another way to look at this figure is also comparing the speed up factor. So how much saving I'm able to do by doing low rank compression versus the numerical accuracy. There is a dotted line, which is a line that is a reference. So anything below that line means that it may not be usable at the end. I'm comparing 4 different system parameters, And it turns out that I can get basically 3 to 4 speed up factor while maintaining a proper accuracy of the application. Of course, when I go beyond a certain accuracy, I may get a better speed up, but the accuracy then drops significantly. So what we've done with this software that we put together in doing this matrix vector multiplication using the Taylor-Rank approximation, we first run on synthetic data sets, right? We run on synthetic first data sets to basically demonstrate the robustness of the code itself. So we run on various architectures, 6 of them here, from Intel, NVIDIA, AMD, Fujitsu. Here we report sustained bandwidth. And we look at how the tile size impact the performance on each of those architecture. So since we report sustained bandwidth, the higher, the better. So, as far as A64FX, we get almost 600 gigabytes per second. This is regardless of the tile size being used. And we can see we get similar performance on MI100 as well as V100 from NVIDIA. However, the A100 NVIDIA GPU gets the most performance beyond 1 terabyte per second for a tile size of NB equal 100. So in terms of time to solution, still on synthetic data set, again, we have similar performance from the Fujitsu A64FX and MI100 from AMD and the NVIDIA V100. And then the performance is much better, as we have seen in the previous slide, when we run on NVIDIA A100. So if we were to compare now the dense versus this Taylor-Rank matrix vector multiplication, we look at the time breakdown of the various phases in doing this matrix vector multiplication with the Taylor-Rank approximation. And we compare against the dense matrix vector multiplication without doing any approximation. So there is already a huge gain from a pure algorithm point of view on each of those architecture, moving from the dense to the Taylor-Rank version, right? And then one can see a clear win, in architecture with HBM with up to 3x or more, depending if you run on ARM or NVIDIA against Intel Cascade Lake. All right, so this was done on synthetic, synthetic data set. Now we're running on MAVIS data sets. This implies that the ranks will be different, right? When we're gonna do compression on each of those tiles, we may end up having different ranks. With synthetic data set, we had constant ranks. And because we do that and we wanna run at the end of the day on real data sets, we require support from the vendor libraries for this batch matrix vector multiplication with variable sizes. Unfortunately, NVIDIA does not provide such kernel, and therefore we can only run on Intel Cascade Lake and A64FX. So when we do that, we can see a performance improvement, moving from Intel Cascade Lake to A64FX. The higher the better. Here we report bandwidth. We get around 450 gigabytes per second on this real MAVIS data set, right? One needs to take into consideration that I'm doing this batch matrix vector multiplication now on data set that may be of different sizes, right? And there are some load imbalance challenges that the library has to handle as well as the system. And still we are able to extract around half of the sustained bandwidth on A64FX. And of course, we have a 3x here performance speed up compared to Intel Cascade Lake. Time to solution, so the lower the better. It's just another way of looking at the previous graph. And we can see that we're getting around 200 microseconds for the A64FX for performing this single Taylor-Rank matrix vector multiplication on MAVIS dataset. So one thing that is extremely important for astronomers is the time jitter, right? Because this thing has to happen, this operation has to happen millions of times at night. So there is a clear concern in maintaining a proper pace, a constant pace for performing such operation, because we are always trying to catch up or predict, in the future. right? So with this graph, we can see that the AMD, the ARM A64FX do have some jitter, and this may be actually a concern, even though it's much less than Intel Cascade Lake, right? So what I'm showing in this graph is the number of runs, 5,000 here, or a bit less than 5,000. And I'm recalled for each of those MADVEC that I'm performing, the time to solution. And so with A64FX, we are much faster than Intel Cascade Lake, but we still suffer from the jitter. And that's, of course, a concern for this real-time application. Another way to look at the jitter is to look at bandwidth. So we record here the bandwidth and scored by the various runs, and we basically calculate the occurrences. So the great plot that we are after here is to have basically a peak where most of the bandwidth score being recorded would be located. And we are, looking into basically the zone here of this graph where we are able to achieve around, 450 gigabytes per second, which is again around half of the sustained bandwidth on the chip. We looked at ROOFLINE performance model on this A64FX, and we think there is still a clear room for improvement. Our implementation use basically MPI plus OpenMP. So we're running an MPI on each MPI process on each NUMA node, and we spawn then OpenMP thread. But we'll be happy to look into further optimizing it so that we can get actually a higher bandwidth. We looked also at performance scalability. So, and for that, we look at various instruments that I have introduced in the beginning, which basically highlight different matrix sizes. And we do basically increase the number of nodes of A64FX up to 16. And we can see that we are able to maintain an ideal, close to ideal speed up for large matrices of this EPIC instrument, for instance, with this orange line here. And MAVIS basically is not able to scale up simply because we are not able to saturate the bandwidth on each of those nodes efficiently. Conclusion, so I just presented a hard real-time computation on Fujitsu A64FX. The TLR-MVM approach is a promising approach, but performance jitter may be an issue. And actually, we'd like to collaborate with our ARM colleague further to try to see how we could reduce that jitter and improve the bandwidth reported on this architecture. So MVM latency is a key design parameter for adaptive optics. So if we can get better performance, we can maximize the science return with no overhead cost. So we have additional margin in the time envelope. This will translate into the ability to implement more sophisticated control approaches to eventually improve again the image quality. So we believe this TLR approach will further reduce the memory footprint, so we can look at even larger matrices that would capture more information in real time from those telescopes, in particular in the context of the extremely large telescope. And we'd like to further investigate also opportunities for mixed precision, TLR matrix vector multiplication, combining basically FP32 and FP16. I'd like to thank you for your attention, and I'll be happy to take any question.